This is the last section of chapter 16, guys. There's only 4 sections in this chapter. I told you guys, y'all were going to like this chapter. We are going to have 2 homework sets. 16.4. So 16.3, finishing talking about the second law and the third law of thermo were the 2 videos that I sent you guys to watch on your own. Okay. So section 2 and section 3, we talked about that property called entropy, okay? That new thermal property that's symbolized by an S. What can we use entropy for? If we look at delta S of the whole ass universe, we can say whether a reaction is spontaneous or non-spontaneous. Guys, it is not very convenient to use that as the criteria for is this spontaneous or not, right? It's not super convenient. So a new thermodynamic property, this thing called free energy, was developed in the late 1800s, okay? This guy developed this new property called free energy. In fact, I actually learned this as Gibbs Free Energy. Okay, Gibbs, like in NCIS. Okay, Gibbs, because this is the mathematician's name who developed this. Okay, Gibbs Free Energy is how I learned it, so that's what I say. And this is the only symbol that makes sense to me. You ready? What's the symbol? Capital G. It's the only one that makes sense to me. Gibbs Free Energy. Okay, Gibbs Free Energy is about the amount. Wait a minute. Let me say this. It's a thermodynamic property, okay? About just the reaction. So I don't have to think about surroundings for this, okay? Not related. What word do I want to use here? I guess about just the reaction. So no part of this is about the surroundings ever, period. Okay. And it is going to let us predict spontaneity. Okay. Why is this called free?
Like excess energy?
Kind of. Like, no, not like that. It's more like a reaction can produce this excess amount of energy that can then be available to do work. Okay. It can possibly push the ball up a hill, right? It can push a piston. Okay. There's some amount of energy that the reaction could give away for free. Is what the word free means. Okay. Free energy is, like every other thermal property we've looked at, a state function. And you guys should know, if it's a state function, that means I only care about final and initial states, which means mathematically solving for a state function is just delta, difference, subtraction. State functions are easy, great, because we can just subtract, right? So again, what we would care about would be, of course, final and initial. What Willard Gibbs, I think his name was Willard. No, it wasn't. Whatever. Okay, Gibbs. What Gibbs did was he actually related this new thing he created, free energy, to properties that we already knew, like enthalpy and entropy. Okay. So this is the first free energy equation that we're going to have today. Delta G. Again, what is this of? Okay, so I'm going to just not write a lot of times the reaction there. Because is it always for the reaction? Correct. Okay. Okay. What do all those symbols mean? Yep. Entropy. Entropy. Free energy, which is the new thing we just are learning about today. What are the units of free energy going to be? They're going to be kilojoules per mole. Okay. Enthalpy, delta H, which we studied a whole chapter of in Gen Chem 1. But enthalpy is also a state function, just like these other things. Enthalpy is final minus initial. Okay. Also, kilojoules per mole. Temperature, it's got to be in Kelvin. Entropy, when we calculate entropy values and we look at standard entropy values, which is what was in the video from yesterday, standard values, all of these values are in joules per mole Kelvin. So you're going to,
That is standard.
standard values have the degree sign. But what I'm saying is even standard values, all entropy values, including those standard ones we saw yesterday, are joules. You can certainly use standard values here. You can use with the degree sign. You can do based on those. Or you can calculate delta S in any of the other ways we did yesterday. Okay. What are we going to have to do this math and get our answer in kilojoules? We're going to have to divide this number, or delta S, by 1,000, right? That will put it in kilojoules per mole Kelvin. So how is this going to predict spontaneity? How is delta G going to predict spontaneity? Well, if delta G is negative, then the reaction is spontaneous. If delta G is positive, then the reaction is non-spawn. Okay. And then if your delta G is 0, your reaction is at equilibrium. Look on your InClass for this chapter 16 and go to number 12. Number 12, I have a table that I want us to fill in together. Okay, so in this table, I'm telling you a couple of some conditions, okay? Let's say I have a reaction where my delta H is negative. What does that mean about the thermicity of this reaction? Delta H is a negative value. That means the reaction is what? Good. That means this reaction is exothermic. Yeah. And if my entropy value, my delta S, that's a positive value. What does positive entropy mean? No, endo-exo is only about thermal. No, delta S itself is not spontaneous or non-spontaneous. What does delta S mean? There's more ways that this reaction has dispersed, spread out, right? Entropy is about spreading out. If entropy is positive, that means the reaction spread out. Okay. So I'm just going to write dispersed, right? Can you predict for me what would be the sign of the free energy for this reaction? Think about a negative and a positive in this equation. Delta G would be a negative value all the time, no matter what temperature it was? Yes. What kind of temperature scale are we using? Are there negative Kelvin values? No, that's the reason why we use it, right? If this is positive and you're subtracting it from a negative number, delta G is always negative, isn't it? Mathematically, it's never anything else. So what does that mean about spontaneity and temperature? It is spontaneous at any temperature the reaction runs at. Spontaneous at all temperatures. What if you have what kind of reaction? Positive delta H. Endothermic. Okay. You remember me telling you 2 days ago that you can't predict spontaneity based only on endo or exo. This is me proving that to you. What if my delta S value for that reaction is negative? Absorbing what? What is delta S about? Dispersion. How dispersed is this matter? If delta S is negative, the correct way to think about it wouldn't say it's absorbing. It's not absorbing energy. It's just not dispersing energy and matter. It is not spreading. It is not spreading. Entropy is not about transfer. So no giving, no taking. Entropy is about just spreading, right? So it's not dispersed, or it just, something happened there, right? So what would you predict the sign of delta G would be in this situation? Always positive? Always positive. At any temperature? At any temperature. Non-spawn at all temperatures. Now here we get to where we can't predict without knowing the temperature. If I have an exothermic reaction, but also my entropy change is not big, it's negative, can I predict? I can't, unless I know the value of T. I can say, so I can't predict. What I can say is that at what temperatures would this reaction be spontaneous? And I'm looking for you to use the word high and low. Those are two options. At what temperature would this reaction give you a negative delta G value? Think about what the value of T would need to be. Low. If this is a very small number, even though I'm multiplying it by a negative number, and then I'm subtracting a negative number, so I'm really adding that value, right? This quantity is very small. I'm still going to end up with a spontaneous, a negative delta G value. Mathematically, I'm going to have a negative value. Low. That should also kind of make sense to us because what we learned about Lié's principle. If it's exothermic, and I'm taking heat away, or I have a very low temperature that the reaction is running at, doesn't it want to keep going even more and more? Sure does. Spontaneous. So what does that mean about non-spontaneous? When you get to high temperatures, that reaction stops being spontaneous. Yeah, that's what that means. Okay. Then, what if both delta H and delta S are positive? Again, I can't predict for certain unless I know the temperature. This situation is essentially the opposite of that situation. At low temperatures, this kind of reaction would be what? Non-spawn. And at high temperatures, now this reaction would be spontaneous. Not necessarily fast. I don't mean fast. Although it probably would be fast. That's not the correlation I want to make here. Okay. How low is low and how high is high? You got to have the numbers to know that. Okay. You just got to have the numbers. Okay. Look at number 13. So that was number 12, filling in this chart. This is very useful to come back to a lot. Okay. Look at number 13. I got a little thought experiment for us. And then we're going to move on to another. We're going to actually use this equation and do some math. But if you look at 13, I gave you an equation for a combustion. It's what's called an incomplete combustion because I didn't make carbon dioxide. I made carbon monoxide. Okay. This is actually why our cars have those catalytic converters, is to keep this incomplete combustion from happening. So our cars produce less carbon monoxide. And it helps catalyze some other reactions that can go on in there. But this incomplete combustion is not something that we want. Okay. How does the spontaneity, so I mean, is it spontaneous or non-spontaneous? That's what I mean. How does it depend on temperature for this reaction? Let's see if we can thought process some of this out. What do you want me to do? Okay. Since it, I like where he's going with this. Hang on. Yes. Guys, combustion reactions are always what? Exothermic. They give off heat. Okay, delta H, negative for this. Delta H is negative. On 13, delta H negative. Okay. What about delta S? Can I make any predictions about the sign of delta S in this reaction? So this is something we talked about 2 days ago, how to predict the sign of delta S. I like looking at the moles of gas. That's a great way to think about. More moles of gas means more entropy. So in this reaction, product side, I get to make 2 moles of gas from 1 mole of gas. My entropy is increasing in this reaction. I also predict delta S is positive. Okay. And so if I said this is negative and this is positive, guys, what can we say about spontaneity and temperature? Spontaneous at all temperatures. At all temperatures. That is another great thing to say. If you know that solid is on one side and on the other side is gas, anytime you go from solid to liquid or then to gas, whatever, absolutely entropy is increasing. That is absolutely a fine way to just predict. Yep, that's all we were doing there. Good. Okay, I'll let you guys think about 14 on your own if you would like to. Do I want to do that? Yeah, because we got to move on. Okay. So, how about at what temperature would it change spontaneity? So these cases where it can be spontaneous at low or high, and then it would not be at high or low, we can calculate the temperature where that happens. Okay, we can calculate the temperature where that happens. That temperature where it flips from being spontaneous to non-spontaneous, or vice versa, that temperature is the temperature at equilibrium. You write that on here. The temperature where it flips spontaneity is the temperature at equilibrium for the reaction. And that can certainly be a phase change. If it's a phase change, that temperature would be known as the what temperature? Like, say I was going from liquid to gas. Okay, everybody think liquid to gas. That's what phase change? Liquid to gas. Vaporization, okay. Boiling point temperature. That temperature would be where that reaction went from non-spontaneous to spontaneous. The boiling point, right? Freezing point would be where it spontaneously goes from what to what? Freezing point. Liquid to solid. That's where it goes from being non-spontaneous to spontaneous, that temperature. If it's not a phase change, we can still calculate equilibrium temperature. The easiest way for us to do that here is remember, if we're at equilibrium, what is true? Delta G equals 0. That word has too many vowels in it, you guys. Delta G is 0. And how can I solve for T? Do a little algebra. Manipulate it around. Can you see something, Loretta? Do I need to read?
What is
at?
Oh.
The at sign.
It looks like a C.
Sorry. There we go. No problem. Temperature equals what?
No.
No negative because we added it to the other side. So no negative, but delta H over delta S. Perfect. Good job, you guys. Okay. Look at number 15. Here's a reaction. And I went ahead and gave you values, number values for delta H and delta S so that we can do math, right? Okay. You guys tell me, looking at delta H and delta S, can you go ahead and tell me, predict if it's a spontaneous reaction? No, we cannot. Why? Yeah, both of these values are positive. When that is the situation, we cannot predict. We can only calculate with temperature. We can say that if it's low temperatures, it should be non-spontaneous. At higher temperatures, it should become spontaneous. So let's see at this temperature what we're dealing with. What temperature are we at in 15? First on part A, we're at 25 degrees C. What is that? Room temperature. What is that in Kelvin? 298 Kelvin. 298 Kelvin. Guys, you have delta H, you have delta S, and you have temperature in Kelvin, 298. You guys can solve for delta G right now. Do the math. Do the math right now for this. Solve for delta G. What can I erase? I don't want to erase the chart yet. I guess I'll erase this. And we'll put the work up here. Because I just love this chapter so much. Thermodynamics just makes so much sense. I don't know why. It just does. And you're like, okay, Miss Poe. Okay. But it does.
Yeah.
Man, all we did was math and ice tables. You're like, no, that's totally different thing, Miss Poe. That's something different. Let's see. What did I get? Hang on. Oh no, I didn't get that, Joe.
I didn't get that either.
Hey, I did you remember to change that delta S from joules to kilojoules? Yep. Guys, this is what's gonna get it. This is what it can easily get you. Is forgetting to change this entropy that comes in joules per Kelvin or joules per mole Kelvin to kilojoules. Yeah. Caitlin, you tattoo that on the inside of your eyelids, okay? And then go up to the light so you can read the words, okay?
Ask someone to read what I would say.
95.7 minus 298 times
142.2 divided by 1,000.
that number divided by 1,000.
53.2.
Positive 53.3 kilojoules. Because this problem didn't have any moles in the unit, so that's, just kilojoules. Yeah. Guys, what does a positive delta G value mean?
It's
Non-spontaneous reaction at this temperature. It's not spontaneous at room temperature. Would it be spontaneous at a higher temperature? It should be. What is the temperature where it becomes a spontaneous reaction? T equals delta H divided by delta S. That temperature. 95.7 divided by 0.1422.
Oh, that's the. She already changed it. Okay.
I'm just working with it in kilojoules. But you absolutely need this delta S to be kilojoules so that the units will cancel. Have to. Okay. 672.99. Okay, What is this unit that this temperature came in? It's calculated in, this is Kelvin. Did I specify Celsius? I did. I want the Celsius temperature. Tell me the Celsius temperature. How do we go from Kelvin back to Celsius? Subtract 273.15. Now, in this original answer, how many sig figs should? Good. So that's marked to the ones place. So when I do this minus this, my answer is going to round and stop at the ones place. And I got the number 400. So I would actually want to write this as 400 with a decimal point specifically written there, so that that's 1, 2, 3 sig figs. That's why I do that. Yeah, that's why I do that. That's why I do that. Okay. Number 16 is the exact same 2 steps with a different reaction. So I'm not going to do that one with you guys right now. I'm going to let you look at the solutions and do it yourself. But just before we move on, looking at the 2 signs of delta H and delta S for this reaction, they are both negative. So you can't predict, can you? What do you suspect the spontaneity of this would be at low temperature? Should be spontaneous. Delta G should be negative. We go to higher temperatures, should have positive delta G. It should get non-spontaneous. You guys can prove that to yourselves by practicing this number 16, okay? No, we're not doing, I'm not doing that with you guys right now. We're moving on. So, standard values in thermodynamics. I discussed them in Gen Chem 1. Your Gen Chem 1 teacher should have discussed them. Delta H with the little circle. Okay, formation values. Or in my video yesterday, entropy values with a little degree sign. Standard values. Standard. Let's talk about that word standard. In thermodynamics, a whole table of values. Where is my table? Whole tables of values have been created and are available in any textbook, on any website, all over. Okay. Lots of different values. All of these are standard values. How do we know they're standard? Well, in the symbol, here, y'all just want to look. In the symbol, you see a degree sign. Standard values. Standard values. What does it mean to be standard? A standard thermo value means you are under standard conditions. What are standard conditions? Anybody remember some of them? Your pressure of a gas, it's technically 1 bar is what the scientific community went to a decade or 2 ago. But 1 bar is almost exactly 1 atmosphere. It's like 1.01 atmospheres. It's almost 1 atmosphere. So we still just say it's 1 atm. Standard pressure. 1 molar if it's an aqueous solution. And the main one I want you to remember is that all of these are calculated at 25 degrees C. Or what? 298 Kelvin, standard conditions. Okay. So we can use standard enthalpy values and standard entropy values. And where do those values come from? A table like the one I'm showing you guys. I used to, when we had textbooks, you had to go look it up yourself. And then on a test, I gave everybody a packet like that. You had to go look it up yourself. Still miss doing that. But these days, what do? I just put the table in the problem for you. Y'all don't even know how easy y'all have it. Y'all don't even know how easy y'all have it, I swear. God, I sound old. Get off my lawn. Okay. If I'm going to use standard values and I'm solving for delta G, the only difference is in the equation, I would be writing the degree symbol. Okay, that's the only difference. All right. So standard enthalpies and standard entropies are calculated using a little formula. Using a formula. For delta H, right? What are you looking at to calculate standard enthalpy change? You guys remember these formulas? Okay, sum. Catherine's like, oh, capital sigma. This is a Greek letter sigma. In math, that means sum. Take the sum. N is the number of moles. Basically, N is the coefficients from the balanced equation. Delta HF, what does F mean? Formation. Formation values are symbolized with this F, and it's the energy released when this compound gets formed. That was Gen Chem 1 topic. Okay, I'm not going back through all that. But you are doing coefficient times the formation for every product in your reaction and adding them together. Sum. Minus what? The sum of the formation values, reactants. Final minus initial. Final minus initial. Same thing with entropy. This is what I did examples of in the video yesterday. Finishing section 16.3, I did examples of solving delta S from standard values. Okay? If you guys can just remember, sum of the products minus the sum of the reactants. And you're going to have to remember to multiply by the coefficient. If there's 2 in the equation, you multiply by that number by 2, right? Let me remember. Let's see, 17 and 18 both deal with standard values. This is the entropy.
Yeah, so it's still the sum of the.
Sum of the entropy for all the products. Got to multiply by the coefficient minus the same deal for the reactants. Yes. You are given a table of values. Can you find delta H? Yes. Can you find delta S? Yes. So then can you find delta G? Yes. What would be the temperature these values would be at, even if the problem doesn't give you this temperature? If we're dealing with standard values, 25 degrees C, right? 298 Kelvin, right? So I don't care which one we work, 17 or 18. Y'all want to pick? I knew you were going to say 17, Caitlin. I already knew it. Let's do 17. She hates when I skip stuff around and go out of order. She hates it. All right, 17. There's an equation. Why does this equation have a half in it? Oof. It is kind of disgusting to see that, isn't it? Guys, it's because this particular equation is an example of what is known as a formation equation. A formation equation. What is a formation equation? Literally, it means forming, and very intentionally, formation is about forming one mole. Okay, but anyways, in these equations, in thermo equations, can you sometimes see fractional coefficients? Yes, yes. So don't freak out because it's got a 1/2 there. Okay, so in this reaction, I got reactants, and I got product, and I got a table of numbers. And I want to know delta G, standard free energy change. And from that, I say, is it spontaneous or not? So you are finding delta G, you're calculating delta G, and then telling me spontaneity. Okay? The way I like to group these summation equations, this is how I like to see it. I don't care if you guys do it this way. I just think it looks less busy on the paper. I don't know. I'm going to do the delta H first. So what am I looking at specifically for delta H? I'm looking at the formation values, right? Okay. What is the formation value for SO2 from the table? How many SO2s do I have? 1 times value. How many O2s do I have? So you can write 1/2, you can write 0.5, whatever you, however you, it's half, okay? Times, what's the O2 value?
0.
Elements don't have formation values. Maybe make a note of that to yourself. If we're talking about formation, elements have 0 value. Why? Because they were already made. By God, by the sun, by the big, whatever you believe in, they were already here. They don't have a formation value. Okay. Oh, I don't need that. I don't write that. Okay. SO3, one of them times negative 395.7, right? What is this sum? It's just this number, right? Product side, there's the total. Reactant side, what's the total? Sum, right? I'm doing the sum. What's the total? Negative 296.8, right? Sum of both sides. Which number gets subtracted from what? Products go first, then minus the reactants. Products minus reactants. And I get a negative number. So technically, and so this, this is the only time. And I'm not super hard on this unit right here. Is it kilojoules? Absolutely, for sure. Actually, the act of multiplying your standard value, which is what unit from the table? Kilojoules per mole. The act of multiplying it by the coefficient is canceling out the moles. And so technically, this is just the amount of kilojoules total. So really, the real correct unit here is kilojoules. However, I have seen on active chem a lot of times, sometimes they will still include the per mole. So I'll accept it as well, because I don't want you to get too confused. So you can either write kilojoules or you can write kilojoules per mole. I don't care which one. I mean, technically it's kilojoules. I mean, technically. So, did you find your glasses, or are these new glasses, Caitlin? Good girl. Okay. I just realized you were wearing them. All right. Let's finish this and then we'll take a break. There's delta H. Let's find delta S. And then we'll change our, you can do it, so you could go ahead and change your delta S, sorry, you could change your S values to kilojoules right here, or you can wait till you get the answer and change that. Like the total and change that. So you're only changing it one time. That's what I like. Let's do that. So again, because you guys know I love to be all color coordinated. Okay, so here we go. So I'm going to do, I'm still thinking about underneath my equation, right? What are my S values? And what are my coefficients, right? 1 times 248.2, right? Let's put that table back here on the recording. Plus 1/2 times. So why does oxygen not 0 here? That is the exact reason. They have 0 formation values. They do not have 0 entropy. Okay? Elements have 0 formation values. They do not have 0 entropy. Okay? Your S value is not 0. It would make no sense. There's only one thing that has an S value of 0, really, and that's a perfect crystal at 0 K, which is the third law of thermodynamics, which was the video I made for you guys yesterday. Oh, okay, and then my SO3. I'm going to have this total, and then I'm going to have my product total 1 times SO3. That's 256.8. I'm going to have that total. Okay. Product minus reactants, right? Products minus reactants. I get negative 94.0 joules per Kelvin. Change it to kilojoules. Divide by 1,000. Move the decimal how many times? A 1, a 2, a 3, 4. No, 3. Again, like before, I've noticed that sometimes active chem keeps the mole there on the bottom. So moles times cal. Okay, whatever. That's fine, right? That's okay as well. What can I do? What's the last thing I need to do? Find delta G? Okay. What was my temperature? 298. It said that in the problem, but if it didn't say in the problem, you should assume it is 298 because we are dealing with standard values. And I got negative 70.9 kilojoules. And so is this spontaneous or not?
Yes.
Delta G is negative. It is spontaneous. Would this reaction be spontaneous at any temperature? How do we, if that's the question that I'm asking you, what is it that you should look at? Remember, we're looking at, okay, so what's the sign of delta H? What's the sign of delta S? And you can go back to that chart for now. But we'll try to get it in our heads, right? If those are both negative, it should only be spontaneous at what? Low or high? Low. Low temperatures. Is room temperature low? Apparently it is to this reaction. Yes. At high temperatures, this should end up non-spontaneous. Good job. Like I said, 18 is identical problem solving. Let's take a break, and then when we come back, I got a new delta G equation to share with you guys, okay? I will put the solution for 18 up here on the slide.